today. But he fixed it. All right, the light doesn't seem to come up, so I'm assuming things are being recorded. So we will continue the discussion on boundary value problems, and in particularly what is called the Sturm-Liouville theory, which is fundamental to boundary value problems. Has any of you already heard of this? All right, so again, I don't characterize this as a graduate level material. It's undergraduate. You will see minor extensions of what we have discussed, but the concepts today and the rest of the week, they lead to bigger things if you are interested, okay? So today we will do just baby steps, and you will see the most general concepts in other courses if that's of interest to you. Okay, so we have seen this ordinary differential equation about thousands of times, right? That's our reference two-point boundary value problem with homogeneous boundary conditions. So we have come up with the concept that this equation has only solutions for some specific lambdas, that we call them the eigenvalues. We computed some basis functions that satisfy this equation for each lambda. We call those the eigenfunctions. And then also what we have done is, by taking combination of those eigenfunctions, we have been able to compute the coefficients by satisfying the initial conditions, right? We took that the initial condition f of x is given by a Fourier expansion, and then we use the Euler equations to compute the coefficients. So what we would like to do is we would like actually to generalize this, and the generalization leads to this concept of Sturm-Liouville boundary value problems. These are two French mathematicians, so we have to pronounce them with a little bit of French accent rather than German accent, as I thought they are. All right, so we have to see what those things are. And obviously, in the process, we will use again separation of variables for this general class of boundary value problems. So our reference problem is really a heat conduction problem. And I remind you here what the heat conduction reference problem was. So A squared was the diffusivity, U is the temperature, UXX equal to UT. We had some homogeneous boundary conditions at x equals 0 and x equal L. And then we had some initial condition f of x. All right, so this will be sort of our reference problem that we would like to generalize. Now, I remind you that we use not just these simple boundary conditions, x of 0 equal to x of L equal to 0, but you can have other sets of boundary conditions. So today we will actually try to generalize the boundary conditions as well, because even if the problem looks simple, by changing the boundary conditions, you get a little bit more interesting things. All right, so what is the first generalization? The first generalization we're going to do is we're going to work with the PDE, the ODE that you see there. This is how our general problem is going to look like. So I want you to pay close attention. I'm not going to do the transient problem in the lecture today, but it's a good idea to see everything here. So can you look at this and tell me how this differs from our standard heat conduction problem? What is new there? Because obviously this is a generalization of heat conduction. So if you see this in your heat transfer class, what is new in this equation? So you can see here, you can see there, you know, even there. So what is new in this equation? What is new in this equation that it comes? All right, tell me the obvious things. So the coefficient here, it is a function of x. So the conductivity is a function of x, okay? So now you may say physically, does that make sense that the conductivity is a function of x? Not really. I mean, the conductivity function of temperature, I can see that, but function of x, you know, I would not go there, okay? But for this, you know, discussion in math, we're going to take that this is a function of x, because if we make p a function of u, which is a function of x, then the problem becomes a nonlinear problem, and we don't deal with nonlinear problems here. We like the easy problems. So, but that's the major first difference, right? The coefficient, the conductivity is a function of x. And then you notice there are two source terms, one that is linear in u, and another source term that depends on x and t. I don't think we did any problem where we had hit source terms. So one of them is a linear in u, and another one is independent of u. All right, and so that's how, you know, one of the generalizations would be to work with this boundary value problem. And so if possible, write it down somewhere in your notes, because every slide today is going to be using this boundary value problem. So I don't want you to forget how it looks like, because this is what we will use. So what other generalization we will be interested to see today will be to change the boundary conditions from essential boundary conditions, so specifying u, or natural boundary conditions specifying u prime, and maybe introduce this sort of boundary conditions. Now, if you take a heat transfer class, nothing is unusual here, all right? So basically, this will be the heat flux. It's proportional to the temperature at that left end. And usually in heat transfer, you're going to have u0 at comma t minus u infinity, where u infinity will be the ambient temperature, all right? So the ambient temperature here, the constant, we got rid of it. So we have a connection of the derivative of u with u, defining a boundary condition on both at x equals 0 and x equal L. So we would like to actually play with these boundary conditions and see if they lead to any interesting cases. Now, h1 and h2 are the heat transfer coefficients, so we will take them to be constant, but in reality, you know, they can change as a function of time. And these equations that you see here actually generalize to all sorts of possibilities, because if h1 is 0 and h2 is 0, you notice you get boundary conditions in terms of fluxes. If h1 and h2 become infinity, then if you divide by h1, right, this term will drop, this term will drop, and you get essential conditions. The boundary conditions are in terms of u. So if you can address this problem with these boundary conditions, you can do all of the problems we have seen before, so we will deal with that. Now, the third generalization, and we will do less of that actually in these lectures, will be to actually solve the problems not anymore in rectangulars, where you can do nice Fourier analysis, right? But somehow in a little bit more interesting geometry. So for example, going from this geometry to something like that, or going to a disk, or maybe to a disk with a hole in it. Being able to work on these different geometries may have implications on the way we did our Fourier analysis in the last few lectures. All right, so we will see a little bit less of that. But again, the techniques will be able to generalize to these problems as well. So what I'm going to do is, OK, so let's restate the problem. This is our general boundary value problem. This is the ODE, OK? This is the set of boundary conditions we have at x equals 0 and x equals L. And the initial condition remains exactly as before. We're going to do separation of variables. I mean, that's the only thing I know, all right? So we're going to assume u equal capital of X, capital of T. Each of them functions of different arguments of little x and little t. So we're going to plug it in this equation, as complicated as it looks. So I'm getting something like that. We agree? ut will become xt prime, right? Ux will become x prime times t. because these are derivatives with respect to x, and u is x times t. So I divide by x times t, and I get separation of variables, t prime over t equal to this big term here equal to minus lambda, where lambda is a constant. All right. So nice. So these are the two ordinary differential equations. So we went from PDEs to ODEs. Nothing new up to now, right? Just an equation that looks slightly more different, but nothing new. And the boundary conditions, we're going to have to do separation of variables there too. So can you tell me what are the boundary conditions implied for capital X and capital T because of these two conditions? What are the boundary conditions for capital of X at x equals 0 and x equal L? Look at this and plug in u equal x, capital of X, capital of T, and tell me what are the boundary conditions for capital X and capital T. Or what boundary conditions can we get for capital X and capital T? If you plug in u equal x times t, what do you get from here? You get that, correct? Yes? And then what would be the obvious condition? I cannot go in this equation, right, and say, oh, capital T of t is equal to 0 at all times, because we're not going anywhere. If I tell you the answer is 0, you're going to tell me, and your course is 0 as well, right? That's not fun. So the boundary conditions will be on capital X and capital X at capital at x, little x equal to 0 and little x equal to L. So basically, we have the first equation has complete set of boundary conditions that they're given by what you see on the bottom. And we don't really have anything for capital of t, because what we need for capital of t is an initial condition. And that initial condition, we have it, because you remember the statement of the problem, we have specified the initial temperature to be f of x. So we're not going to deal with the initial condition until the end. So we will try to find eigenfunctions for capital of x, write the solution as a combination of basis functions that come from these eigenfunctions. And then at the end, we're going to compute the coefficiency of that linear combination by applying the initial condition being f of x. Okay? So that will have to wait. But right now, we have two ODs. And for capital of x, we have to solve that nice problem, right? Now, you may say, that doesn't look very nice. Looks very complicated. So let's see what is going on. So this is obviously not as easy as this problem here, all right? But you have to trust me. The same way we computed eigenvalues for this nice problem, we should be able to compute eigenvalues for this nice problem. And the same way we computed eigenfunctions for, here we got sines. We should be able to get something out of this. Maybe they're not sines and cosines. Maybe they're something else. Okay? So what I want you to actually start thinking right now, right, is in a lot of the problems we work with, like this problem, the basis functions were sines, and basically we got Fourier expansions, sine Fourier expansions, or cosine Fourier expansions. I want you to think about this problem leading to eigenfunctions that can be some weird-looking functions, but those weird-looking functions are embedded in this ordinary differential equations. They are the eigenfunctions of that equation. And they are complete eigenfunctions. They form a basis, so I can actually write any function as a combination of those eigenfunctions. Now, you may say, why should I write this function as a combination of the eigenfunctions of this rather than using sines and cosines? Because, you know what? There may be some merit if you work with this particular problem, working with the eigenfunctions that are derived from this equation at the top. It would be beneficial because those eigenfunctions will be orthonormal. So lots of the calculations will look trivial. If you use sines and cosines, they will not be natural to this problem. All right? So we will have to see why that is the case. So, but the idea here is, in a lot of PDEs, we're going to be getting these ordinary differential equations that have a set of eigenfunctions, and we will be able to write a solution to the original PDE problem as a linear combination of those eigenfunctions. And the set of the eigenfunctions we will get will be infinite. All right? So remember, when you solve AX equal lambda x like an eigenvalue problem, for a given size of A, you get a finite number of eigenvalues and eigenvectors. Here you get an infinite number of eigenvalues and an infinite number of eigenfunctions. Okay? An infinite number. So you may say, but if it's an infinite, what do I do with it? Well, the nice thing is, you know, maybe this series converges and you don't have to use the infinite values. But the bottom line is, this is a differential equation, right? It's not an algebraic problem. So you will not have a finite number of eigenvalues and eigenvectors. We have an infinite number. All right. Let me just say that if I only concentrate on the steady state problem, this is what we worked on like maybe 10 lectures ago or 15 lectures ago. We worked on ordinary differential equations that look in this form. The only thing I want to tell you is, if you go back and you think of all the methods for solving this equation, trust me, you can take this equation that you see there, you can actually put it on this form. All right? So basically, this is a much nicer form because it will reveal a particular structure, but a lot of the problems we looked in the past, right, can actually take this form. I mean, obviously, there's no parameters here, but I can always plug in a parameter, right? I can put lambda times r of x, y equal to 0, and I can make this equation 1 to look like 2. But I want you to basically not to think that what we did in ODEs, second order ODEs, is very much different from what you see here. Here, there is a particular form of this equation, and we will try to take advantage of that form. All right. So let me start with a trivial example first, and then we will go back to solve this general boundary value problem. So what I'm going to do is I'm going to take our easygoing problem that we have used in the past, y double prime plus lambda y equal to 0. But I'm only going to enhance the boundary conditions to one of them at x equal to 1 to be a mixed boundary condition involving both the derivative and y. All right, so we're going to use a mixed boundary condition to see if it adds anything interesting in solving this problem. So obviously, does this problem does it fit in this form? Does it fit in this form? Can you tell me the particulars here to get that equation that I had before? How much q has to be? I remind you the differential equation was y double prime plus lambda y equal to 0. So how much q has to be? 0. How much p? 1. And how much r? 1, right? So that's a very easy problem, but still it fits in that general category. And so let's try to solve it. Since we don't know what values lambda has, let me assume that lambda equal to 0. So if lambda equal to 0, the equation becomes y double prime equal to 0. So the solution is linear, right? So if you put y at 0 equal to 0, so obviously C1 is going to come equal to 0. And then from this thing with the derivatives, well, I missed here. One has to be C1 and another one has to be C2, right? So we will correct this. So basically, both coefficients are equal to 0, which means lambda equal to 0 is not an eigenvalue, right? For lambda equal to 0 to be an eigenvalue, the eigenvector has to be non-zero. But here, everything is 0, so lambda equal to 0 is not fun. So we're going to take lambda to be positive. You agree that the solution is sines of square root of lambda x and cosine of square root of lambda x, right? So apply some boundary conditions and tell me, what do you think? what does y of 0 equal to 0 means here? So if you put x equal to 0, this will drop. So what can you tell me about C2? C2, 0? All right. So, and then you have, so only left with this term. So you're going to have the derivative of sine, which is a cosine, plus the sine. So you're going to get something like that. So immediately you can see that the eigenvalues can be computed by solving this nice equation. All right? Now, we just changed a little bit the boundary conditions, so now we don't get nice eigenvalues, right? The eigenvalues look very complicated. But nothing is complicated, all right? By the way, notice that this cosine of square root of lambda cannot be equal to 0, because if this is 0, then the sine of square root of lambda is 0. You're going to have the sine and the cosine to be equal to 0. Makes no sense, right? Okay, so the cosine is not 0, which means I can divide by the cosine. And if you divide by the cosine, you get this nice equation. So if I give you this as a homework, and obviously, regardless what homeworks I choose tonight for next week, you will get equations like that, and most probably more complicated. So how do you solve for lambda if I ask you to do this? I mean, you know, if you go home and you have to compute the lambdas that solve this equation, do you think you have one lambda only? I mean, a trivial way to see it, right, is to actually do the following. Plot, the x-axis here is square root of lambda, plot the function square root of lambda, which is linear, because my independent variable I have used here is square root of lambda, right? This is like the line y equal to x, this straight line here. And then plot minus tangent of x, which are these nice curves that you see there that vary asymptotically between, in the intervals pi over 2 and 3 pi over 2 and 3 pi over 2 and 5 pi over 2, etc. So can you see now that there are infinite eigenvalues, right? And actually, if you look carefully, as lambda increases, it is sort of, you know, you can identify that the square root of lambda is very close, becomes closer and closer to these vertical lines that you see here, where you have the asymptotic values for the tangent of square root of lambda. So let me put the results up. The first three eigenvalues that will be inaccurate, actually, if you try to generalize and use the big formula that I have below. But lambda 1, lambda 2, lambda 3 are given by these numbers. And lambda n, for n equal 4 to 5, etc., approximately is 2n minus 1 squared, pi squared over 4. OK? Approximately. Now, if you use a computer program and evaluate this exactly, it's not going to give you this formula. But, you know, if you plot it this way, you can actually see that, you know, as n gets bigger and bigger, these values of square root of lambda, where you have this tangent blowing up, will be corresponding to these values that you see here. All right, so you can see, for example, n equal to 4, what is that? So what is the square root of lambda of this? Actually, I don't have the plot. The square root of lambda is missing, but it's here, actually. All right, so for n equal to 4, you have 7 pi over 2. And you can see here, right, somewhere up there, can you see that that value is close to 7 pi over 2? Yep. I'm saying is this formula can be used also for approximation of the earlier values, but you can see, like, for example, for n equal to 1, it's not very good yet. For n equal 2, it gets a little bit better. N equal 3, much better. So for n equal 4, you can trust that this formula here is the correct formula. And on the bottom, you see the eigenfunctions now, right? So once you compute, you remember our original problem, it was y double prime plus lambda y equal to 0. So obviously, the eigenfunctions are sines of square root of lambda x. So the eigenfunctions are sine of square root of lambda n x. So we have an infinite number of those. And then, of course, the last thing you need to check is if there are any eigenvalues with lambda negative. So if lambda is negative and you set lambda equal minus some positive number, the solutions to this equation would be exponentials, right? And I write them instead of exponentials with hyperbolic signs and hyperbolic cosines. And you can actually do exactly the same algebra as before and see that the equation to solve for lambda is given by this nice formula. So an easy way, of course, is to write some iterative method, and you should investigate those because you may need them in your homework in solving these equations. But another easy way is to actually plot these equations. If I take the square root of mu here as the horizontal axis, if I plot this straight line that you see here, all right, versus minus hyperbolic tangent of x, which is like that, and you can see the only intersection of the two things is for the value 0. So really there are no negative eigenvalues for this problem, okay? So basically what we computed before is the only solutions we can get. You may ask me, do I have complex eigenvalues? So good news, the particular problems we're working, the general class of problems, not just this problem, don't have complex eigenvalues. And actually, I'm going to prove it today, okay? So we don't have to worry about that. Okay, so changing the boundary conditions for a trivial problem, we got a little bit more interesting things. So we need to go back now to the more general problem. And the more general problem is this ordinary differential equation. And again, the only difference is the coefficient is a function of x, and there are source terms. You remember in the original equation there was a capital F of x and t. I took it equal to 0 here. But I basically have two terms here that are written in this form, okay? So this is the problem we want to solve. And we're going to take very general boundary conditions. So I'm going to use coefficients alpha to describe this relation between y and y prime at x equals 0. And we're going to do the same thing at x equals to 1, okay? So we're going to try to solve this problem. Now, let me go back, right? So what I'm going to do is I'm going to try to generalize this problem notation-wise to remind you that this problem, as complicated as it may look, it's actually a very familiar problem. So look at this equation carefully, all right? So you have p y prime, and then the whole thing derivative, minus qy, plus lambda r y equal to 0. So I want to look at the first two terms with a minus sign, actually. So how about if I do the following? I'm going to define an operator L that when it's applied to the function y, it gives me minus py prime prime plus qy. So if you use this as a definition, can you tell me what is the form of the differential equation? Again, if I use this as a definition, as L of y to be this, can you tell me what this equation looks like? Remember, I use minus signs here. So what are the two terms then together? Minus L of y, all right? So the equation becomes L of y equal L lambda r of x times y, right? Now, you may ask, big deal, you simplify the equation, but you're hiding all the complexity there. But is there any reason to write this equation like that? Does it remind you anything? Look at that equation and tell me if it reminds you anything. How about if L was a matrix, right? Because an operator you apply on a function, with a matrix you apply on a vector. So if L was a vector, what does this equation look like? AX equal lambda x, right? How do we call that problem? Eigenvalue problem. So immediately you can see here that lambdas are the eigenvalues, but not of the matrix A. There's no matrix here. They're the eigenvalues of this operator L. That's a new concept, right? Eigenvalues of an operator. You can think of an operator as being an infinite matrix, right? An infinite matrix. And of course, Y will be the corresponding eigenvectors of this equation. So immediately, you can see an analog between our ordinary differential equation, this Sturm-Liouville problem, and the eigenvalue problem from linear algebra. Now, I need to put some constraints on all the functions to make all the theorems that I'm going to show you to work. So let me just state some of the constraints. You need to have P, the derivative of P, Q and R to be continuous on 0 to 1. I mean, if you think about it, right, it makes sense. P here comes. If you take this derivative, you're going to have two terms. One will involve P, the other one will involve P prime. So I want P and P prime to be continuous. I want the same thing for Q and the same thing for R. And also, I want to have P of X greater than 0, which, if you think about it, makes sense because the conductivity cannot be negative, right? This problem, we are going to have difficulties to solve it if the conductivity is negative, okay? And then you will see why we're going to have to assume that R has to be greater than 0 on 0 to 1. I actually want you to remember this in case I forget, because when we do the derivations, all of these things are going to come to play a role. So continuity on everything, including P prime, and then P has to be greater than 0, and R has to be greater than 0 on the interval 0 to 1 that we work on. And our boundary conditions are the standard boundary conditions. I'm not going to bother you with this terminology here that the boundary conditions are separated. Basically, the boundary condition on the left involves only the values at x equals 0. The boundary condition on the right, it only involves the values at x equal to 1. But actually, you can have a boundary condition that involves y at x equals 0 and y at x equal L if you think about it, right? If you think that you have a string and you bring it all the way around, you can have periodic boundary conditions, and the boundary conditions can become what is called separated. So I'm going to use this later in the lecture, but right now we work with the standard boundary conditions that you see down there. Okay, one of the most important now derivations in the lecture today, extremely fundamental, right? So I'm going to take two arbitrary functions, u and v, right? They're arbitrary, but they have continuous second derivatives, all right? Which means basically I can differentiate them, and the second derivatives are continuous in the interval 0 to 1. So apart from that, they're arbitrary. Now, where this constraint comes that they are continuous second derivatives, because if you remember, if you look at this problem, right, u and v are like y, and I see they are second derivatives, right, and first derivatives. So I'm going to take two functions that have continuous second derivatives, okay? They're arbitrary up to now. They're just continuous second derivatives, all right? I am going to compute the integral of L of u times v in the, and I integrate this from 0 to 1. And I write L of u explicitly here. L of u was minus p u prime prime plus qu times v, all right? U and v are arbitrary functions. The only thing they do is they have continuous second derivatives. No relation to the differential equation. They are arbitrary. Now, I'm going to make them to have some relation with the differential equation. And that some relation is going to be, let me just actually eliminate, that condition is going to be that somehow both u and v satisfy the boundary conditions that you see on the bottom. So they're not the solutions to the problem, but they satisfy the boundary conditions. Okay? Now, why do this? Because let's see what's going to happen. So I computed this integral L of u times v that looks like this. And you know what I'm going to do is I'm going to take this first term, and I'm going to do integration by parts twice. You remember integration by parts? Can you tell me if you integrate by parts, the final term that is going to stay inside the integral that results from this, how is it going to look like? You integrate by parts twice. So how is that term going to look if you integrate twice? Forget the boundary terms, right? Just the differential term inside the integral. How is it going to look like if you integrate twice? Take a guess. I mean, when you integrate twice, the first time, you will get p u prime, v prime. Yes? When you integrate once more, what are you going to get? You're going to get p v prime prime times q. Yep. Integrate twice by parts. So when you integrate by parts twice, you should do it because it builds character. I had to do it myself before I came here to be sure that the equation is typed correctly. So when you integrate by parts, this is what you get. You get, instead of having u, now you have v, and instead of having v, you have u, all right? This term is already symmetric, q times uv, you don't touch it. And then you get two boundary conditions. This first term evaluated at 1 minus the value at 0, and this evaluated at 1 minus the value at 0. So I'm expanding this, all right? And it takes this nice form. Now, you have to believe me that if u and v satisfy the boundary conditions of the differential equation that we had in the previous slide, guess what is going to happen to this whole first term if u and v satisfy the boundary conditions by a miracle of nature? What do you think is going to happen? They will disappear. They will go to 0, all right? And so assuming, of course, that these coefficients A2 and B2 are not 0, so I can divide by them. So it comes out. And again, I'm not going to spend time to do simple algebra. If you plug in u prime and v prime from these two equations here at the ends 1 and 0, then the whole thing cancels out. And it cancels out, and the Lagrange identity is what you see on the bottom. L of u, the integral of L of u times v is the same as the integral of L of v times u. Don't you like this? There must be something interesting there, right? And remember that u and v, what are they again? U and v are what functions? They're arbitrary, except the fact that they have second derivatives that they are continuous, and also satisfy what? The boundary conditions. They are not the solutions to the problem. They are arbitrary, all right, but they satisfy this identity that Lagrange came, it was the first one to come with, all right? L of u, v, u, L of v equal to 0. So basically, you know what? Seems somehow you can move L from u to v, right? And from v to u. And any name for that actually in practice, you know, for those who know mathematics? How do we call this operators that we can do this? Looks like in a product, but how do we call the operators that have this nice property? What do we say about L? Come on, you know the name. Nonlinear. I mean, all operators are linear that we work with, but there is a name, a nice name. Huge class of problems in engineering and the sciences with this type of operators. What name? Throw me names. Nice operators, that's a name, nice operator. What other names? Come on. A really nice operator. Actually, they are very, very nice operators, so how do we call them? Say it again? Yeah. Actually, you know what? If this was metrics, a matrix, how will you, if AU V is equal to U AV. Actually, you have to put some dot products there, right? Makes sense with matrices. How will you call this if this was a nice matrix? Let's say a matrix with real elements. If you have U dot with, I'm sorry, if you had AU dot with V equal to U dotted with AV, how do you call that matrix? That you can reverse U and V. What matrix will that be? Say it again, what? She doesn't know, tell me. A matrix that has this nice property, U dotted AV equal V dotted with AU. Something simple, I mean, a matrix, I'm not, just for matrices, real numbers. What's the definition of the transpose of a matrix? Will a matrix that has A equal to A transpose satisfy that property? Looks like. All right, so these operators that you see here, they call adjoint operators. Right, you heard that name before? Adjoint, self-adjoint. Okay, so huge class of problems, and they are very, very nice. Without them, cannot live. Life gets very complicated. Okay, all right. So they are the adjoint operators. And as someone said, I can write this in an inner product form if you like. If you define this, the inner product between functions like that, you can write this L of U V equal UL of V, right? And by the way, think again of linear algebra. If you take the inner product of AU with V and of U with AV, when is that? When are they equal? Isn't it? When the matrix is symmetric, will that do it? All right, here, there is no such a thing as symmetric. It is self-adjoint operator. Now, by the way, you can extend these ideas to functions that they are complex. The only thing you have to do is, in the inner product, you have to define the inner product as the integral of U times the complex conjugate of V dx, okay? So now, actually, I should not put a 0 there. Where did I put a 0? Okay? So there's no 0 there, right? But this is correct, okay? So the point is, in taking this inner product, I can have my functions U and V to be complex. The only difference is the inner product has to be U times the conjugate of V, okay? Assuming all the other functions in the differential equations and all the coefficients in the boundary conditions were real. All right. So now, obviously, we're going to have to state a number of theorems for this particular type of operators. And just as a reminder, all right, as a reminder for our trivial problem, the eigenvalues were n squared pi squared. The eigenfunctions were sines of n pi x. And if you look actually carefully on this thing, does this problem satisfy the Lagrange identity? I mean, this is like the most trivial example we did before. Does it satisfy the Lagrange identity? How about when you go home, right? Look at the operator L, what it is, because there is a lot of terms that are not there, and the rest of the terms are equal to 1, and you will convince yourself that the Lagrange identity is satisfied on this problem. All right, theorem 1. We're looking at the general Sturm-Liouville problem, right, with the general boundary conditions. So theorem 1 says that the eigenvalues of this problem are real, and the eigenfunctions are real. Okay? You remember the corresponding theorem in linear algebra for symmetric matrices? What was it for the eigenvalue problem? That symmetric matrices, what eigenvalues? Real, right? So, you know, this is a generalization. There's nothing new here, all right? But we can generalize from linear algebra to functions and operators. So what I'm going to do is I'm going to assume that that lambda in general is a complex eigenvalue. The eigenfunctions, we're going to assume that they're also complex, all right? And so I'm going to write a Lagrange, so I'm going to take actually phi to be an eigenvector, right? One of the eigenvectors of my Sturm-Liouville problem. So phi is one of my eigenvectors. So obviously, it satisfies the boundary conditions and the differentiability conditions. So if I put, before I had arbitrary functions u and v, so I put the same phi here, right? So L of phi equals phi of L of phi, the inner products. And I'm going to allow complex functions here, all right? So what is L of phi? Phi is an eigenfunction, is lambda times R of phi. You remember it's the solution to how my eigenvalue problem looks like, right? My eigenvalue problem is L of operating on phi is lambda times R times phi. And I'm doing the same thing for L of phi there. So lambda times R times phi. And I can simplify. I can move from properties of the inner product lambda outside. The second phi here is going to become a complex conjugate, right, by the definition of the inner product. And this, it will give me a complex conjugate of lambda, which you see here, a complex conjugate of R, which is R because we're going to assume that all the coefficients are real, and then a complex conjugate of phi, which you see there in the middle. So if I rearrange this, I get this wonderful thing, that lambda minus lambda complex times this integral equal to 0, and this integral is, because phi is u plus iv, is u squared plus v squared times r dx equal to 0. And now with confidence, I can say lambda equal to lambda bar. But I need to have a particular assumption that we used before for r. For this integral not to be 0, what do I need about r for that integral not to be 0? You remember there were some properties we stated for the coefficients, and one of them was saying that r has to be positive, all right? So r has to be positive, and if r is positive, this integral is greater than 0. So lambda equal to lambda bar, so the eigenvalues are real. And actually, on the second theorem, you can prove that if you have two eigenvalues that they are distinct, the corresponding eigenvectors are orthogonal, exactly like in symmetric matrices. But notice now something extremely interesting and wonderful. The orthogonality does not mean phi1 times phi2 dx equal to 0. It means phi1, phi2 times r of x. R of x is like a weight in defining this inner product, right? It's part of the differential equation, and it comes as a weight in defining the inner product. So if you have two distinct eigenvalues, if lambda 1 is not equal to lambda 2, then this integral of phi1, phi2, r of x dx equal to 0. That's orthogonality. And how do you prove this? You start with two eigenvalues, lambda 1, lambda 2, that they're not the same. The corresponding eigenfunctions are phi1 and phi2. You use the Lagrange identity for phi1 and phi2 this time. You expand them in terms of inner products. You put things in order. We already have proved that the eigenvalues are real, so the complex of lambda 2 is lambda 2. And when you put things together, you get this wonderful formula. And because lambda 1 is not equal to lambda 2, that big integral is 0. So that's what you get. You get orthogonality of phi1 and phi2. But orthogonality involves an r. This is very fundamental to these problems, right? And remember, you know, when you define inner product, there are some fundamental equations that an inner product has to satisfy. And you can go back and check that defining an inner product like that, it satisfies everything. So, you know, I can, right now, there is a very particular inner product for this boundary value problem that makes sense, and that's what you use, all right? you're not going to go and use your own inner product. You use the inner product that the differential equation demands. So this parenthesis is not 0, so that integral is 0, and the theorem has been proved. Theorem 3. For each eigenvalue, there is only one eigenfunction. All the eigenfunctions are linearly independent, and you have an infinite number of the eigenvalues and the eigenfunctions. So if you order them like this, and you take the limit of lambda n as n goes to infinity, that limit is infinite. Okay, so you have an infinite set of eigenvalues and eigenvectors. You may say that's bad news, but it's expected, right? It's you work with functions now, you will not have a finite number of eigenvalues. And again, if you want to convince yourself that these things make sense, for our simple problem, these are the eigenvalues. They are infinite. Lambda n goes to 0, right? And actually, you can see the orthogonality. What type of eigenfunctions do we get for this problem? Remind me. For y double prime plus lambda y, what were the eigenfunctions looking like? Sines of square root of lambda x, right? And what is the orthogonality property of sines? We did this when we did Fourier analysis. It's the product of sines for two different coefficients gives you 0. And is that what we had before? Yes, because r equal to 1 on this problem. Okay, because r equal to 1. All right. Now, what you would like is, right, you would like, we don't even know when the light is going to go off because it has been off all the time. So we would like these eigenfunctions to be normalized. We have magnitude equal to 1, and magnitude equal to 1 means this equation here. Okay? So let me just finish by taking those sines functions for our simple problem. And so the eigenfunctions were sines of n pi x. And so if you take, if you multiply this with some constant and you try to normalize them so they have magnitude equal to 1, it comes out that K1, that the normalized eigenfunctions for our simple problem, they have a square root of 2 there. So if you see weird coefficients in books and textbooks, you know, they are to make these functions orthonormal. And, okay? And all right, and what I was going to show you, if I can finish, I'm sorry, this is a little bit different problem. So in this problem, it's the same differential equation, but now one of the boundary conditions is a mixed boundary condition. So if you have that and you try to make the magnitude of the eigenfunctions to be equal to 1, you basically get this wonderful fiends, okay? Now, what I want you to do is, and I'm going to come back to this on Wednesday, how do we take advantage of the orthogonal property of the eigenfunctions to expand the concept of Fourier analysis, not to sines and cosines, but to basis functions that come from this Sturm-Liouville type of problems. All right, so I'll see you on Wednesday.